this scale here is volume, the volume of the water in the lake. The bottom one here is the area. So what we want is a very defined correlation of area to volume. If we have that, we can measure a lake's area from the sky, and we can work out the volume below that. And you'll see here a really great result. Our red dots for the smaller lakes fit beautifully on the line from the blue dot. So now, this result actually is good enough that they can look at any time of the year with a satellite photograph and work out pretty reliably how much water is in the lake. It's actually a really good result. And I say it's all done through a student project, working at the University of Leeds, and taken out there and done and deployed with some great results. So also, of course, open spaces are great for air vehicles to fly around and explore things. We do lots of work with drones. We don't make drones, we modify drones to do things we want to do. It's called a marsupial robot. We have two robots together. We have a vehicle that's flying around, another vehicle underneath it, it lands, undocks, and we drive away. Unfortunately, the camera here can't see that step. It's a bit unfortunate, but it's an example of two vehicles together. Then we fly off. You can imagine you go somewhere dangerous, drop the robot off. Get rid of that to get a bit accurate. Another example, so yeah, we can do that one. Another example here, we can use drones to actually go away and deposit material. So here we have a 3D printer on a drone. We can fly somewhere and we can deposit some material to repair that structure, to maintain it. So we're printing here with a drone. Here we're applying some plastic material. We have some really state-of-the-art stuff where we can 3D print in building material effectively. So micro building material we can do now. And the idea is we'll fly somewhere, we'll go and deploy some material. So if something's broken, we can patch it quickly, and then we can fly off again. That's the idea. Drones are great for short-term flights. They're great for kind of like going thing, but typically they last for around about, maybe at best half an hour for flying. That's fine for a particular thing, but in many applications you want long-term surveillance. You want to be over a spot for a day, you need a fixed-wing air vehicle, so quite a big air vehicle to do that. So we're interested in how you can have air vehicles that can be land in places and be retrieved. So for example, I'm going to show you here, this is the conventional way you would try to launch and capture quite a large vehicle. So it's about a metre wingspan here, but it could fly for a day, for example, so it's quite big. So, but right now, to launch it without a runway, you go on the back of a truck, really fast, it flies off. It flies around, but then to get it back again, you have no runway, you chuck a parachute out. And of course it works fine in a field, but if you want to autonomously fly, land, recharge and relaunch, you can't do it. If you want to fly over a city, you can't do it. So this technique is just not viable for larger wingspans. So there are other ways of doing it. So if you look at smaller air vehicles, what you can do is you can try and catch them. This is actually a person trying to catch them. He's not very good at catching them. It's not, I don't know this person, it's someone I don't know. But so it comes in and you can just try and catch it. He's not very good at catching it. He's getting better. It's quite hard. And of course the challenge here is, in order to catch it like this, it's sucking the actual speed's being taken out of it, so it's coming in quite slow. The slower you fly, the less accurate you are. So ideally, you want to take a 2 metre long air vehicle, fly at a robot really fast and catch it. So we didn't have to work with trying to catch very fast moving air vehicles. It's a current project, we've not got the answer yet, we're trying to do it. One of the challenges here though is how do you catch it? So if I flew an air vehicle, had a spring and a damper on here, we end up with very sharp things called jerks. So I guess you know about, you've got position, velocity, acceleration. The differential of acceleration is jerk. So there's a fourth one on that. Jerk is very important. Jerk is really a measure of how a structure is being shocked. So if you were to catch an air vehicle yourself, badly, you would put on very high jerk, and the wings might fall off. So we're talking about going really high speed here. So we want to catch the air vehicle over the shortest possible distance. That means really stressing it to the maximum. So very hard to define this, what you're doing. So we've defined this kind of force profile. It's like catching a cricket ball, if you like. So it comes towards you. Initially, you apply a small amount of force. At the midpoint, you're probably accelerating quite a lot. And then towards the end, you're providing less force. So you want to have this kind of profile from a robot that can catch things. If you do that, you get a beautiful smooth, you don't get zero jerk, but it's a smooth jerk, quite well defined. And you can see here we're doing some stuff, I won't go through all this stuff here. One of the things I should say though is when you're catching something, quite often you don't know how heavy it is. And that's really important. So if mathematically you're defining a force against time, if you try and decelerate an object with the wrong force, either it will not decelerate or you'll push it out again. So it's very important. So we do some stuff here. So the moment you catch it, you start measuring its properties, and then you can change how much force you apply. Like a football. If someone throws you a football, it looks like a ball, but in fact it's quite heavy. The moment you touch it, you'll feel that and go, oh, it's quite heavy, and you will change the way you're doing it. So we have to do that. We can't just say it's a ball no matter what. We have to measure what we do when we feel and touch what's coming to us. So you can see here we're adapting. So this was our original force profile. We're changing it as we go forward to different things. A bit short, so I'll skip that one. So can I go on to number 2, please? So I have a presentation in 3 parts. Because of the videos, it was too big to put in one part, so bear with me, I'm just changing across to the second part. So it's just part number 2. Okay, yes, so part number 2. So there's a lesson there, so I tried to put them into one big slide, but it all fell apart, so that's why we've got 3 slides here. I've talked about the general case of large spaces. There's probably maybe a more useful space, confined spaces are more useful. So in this case here you have, for example, a pipe. It's small. You've got to build a small robot. You've got to somehow get it into there. It's quite difficult. So it's a different kind of problem. So in the open spaces, it's about endurance, traveling. In the small spaces, it's much more about dexterity, much more challenging. I want to talk about our most famous project probably, which was to explore the Great Pyramid of Giza. So if you look at obviously in Egypt, these beautiful Great Pyramids out there, but there are still many questions that nobody knows about. So we're trying to answer these questions using robots to get into small, confined spaces. If you look at the pyramid, beautiful, beautiful structure. If you could magically chop it in half, that would be great, you'd see lots of things. You would see it has 2 central chambers, and it has these, what they call air shafts. From the king's chamber, the air shaft goes out. From the queen's chamber, the air shaft doesn't go out. So it goes from the center point here towards the outer casing, but doesn't leave the pyramid. So the big question here is, what's this? Is it 20 tons of stone? Could be. Is it a secret chamber? It could be. Nobody knows. But these shafts, they're only 20 by 20 millimeters. So really small shafts. And there is genuinely no way to find out what's going excuse me, what's going on, apart from using a robot. So yeah, we're trying to do that. So you can see here the kind of scenario. These small squares here, you must go in this shaft and climb up. The shafts are mostly beautiful and straight, but at points they have things sticking out. So at points here you've got a block move sideways. Small effect, but it affects what you're doing. And this one here, a step here. So, and bear in mind these photographs are taken going upwards, so it makes it more difficult to try and climb in these shafts. So you have to get in there to climb the shaft up. So we know that the shaft ends up here. So what we're trying to do is we're trying to find what's going on here, and ideally what's going on here. We don't know what's going on, and because you have to climb the shaft, you need a reaction force. So you can't just get a radio controlled car and put it into the shaft and drive it up. It's not enough force. So you have to push top of the shaft, push bottom of the shaft to get enough traction to be able to climb up. So it's quite a difficult design decision. So you can't do this. And we spent a lot of time trying to design different ways, trying to make the simplest possible solution. But it's actually really tough, especially when you've got these steps. So if you were to do this, and there's a step here, you can't get over it. So how do you do that? So we took inspiration from biology. This is from the what's called inchworm, a really small insect that grips at one point, the body flexes, and the other point grips. They're amazing little things. So we were inspired by this to make a robot that can climb. So our robot looks like this. So rather than the little feet that dig into the wood, we have these things that go out. So we have front pads that go out and back pads that go out. And by a sequence of extension, retraction on these things, you can see here initially we release this one here. The body can change length. This carriage goes forward and backwards. And you can gradually inchworm your way up the shaft. The really good thing about this is that when it touches the wall, the point of contact never scrapes, never drags, never gets damaged. You push it, you hold it, then you release it. If you were to use tank tracks, if you were to use wheels, you scuff and scrape the surface, and that's bad. You can see here in more detail, using 3D printing to make the most simple thing possible. We have different wheels here. You'll see here we've got a big wheel on the front. It looks kind of strange. When you want to go over a step, drive over a big step, you need a big front wheel. The bigger front wheel, the easier it is to go over it. Once you're past the step, it's much easier to get up there. So we have a different size front and back wheel. The back wheel's being smaller to make it easier to be more compact. The front wheel's being big because it must climb this step, which is quite difficult. Here's a reminder here, so big front wheel to climb that step. We make it via a central metallic spine. We have a drill on here, we have a center motor here, so what we do, this can drive forward and backwards on this spine. We have another thing here, this is actually a tool. You can deploy drills, you can deploy cameras on the same thing, but these things go forward and backwards. We add on the 3D printed plastic parts on top of that. We have a drill, we built a custom built drill. You would think that it's quite easy to have a drill. The problem with limestone is quite soft. So all of the drilling technology you can buy in the shop didn't work. We actually made our own drill by taking tubes and putting on diamond cutting teeth to make specialized material to drill this. And you can see here, it works quite well because you're at an angle. This is just a test in the lab, by the way, a lab test. Because you're at an angle, the powder falls out, and that means that you don't get clogged. Normally if you did this, you get all the powder would get in the way. The powder falls out, you can grind away. It's a really nice, simple way of cutting material. We also have cameras. So cameras that you can put, so you drill a hole, then you have a camera that you can put through. There's a flexible camera that looks around. So you want to go and explore that space that you find there. So we do it with this tendon stuff here. So we have a camera here, we have tendons. Upon the tendons, it can steer and move in different directions. You can see us here inside the pyramid, so it's a great place to work. You can imagine it's an amazing place to be. So you can see all the computer stuff going on here, and here's that entrance here. So this is where we put the robot in. It may as well be in space. Once it goes in there beyond your arm's reach, it's gone. You're not going to get it out again. If it gets stuck in there, you spend the rest of your career building robots to rescue it. So it's a very high pressure, very high different stakes situation. So it must get in there, it mustn't fail, it mustn't get stuck. So the worst case scenario is getting stuck. So failing is bad, very bad. Getting stuck is a massive disaster, so you mustn't do that. You can see here, it's being deployed into the pyramid. So as you climb the shaft, you see the different features of the pyramid. So you can see here, this is a red line here, is an original builder's line. So when they made the pyramid, they used red paint to define the outside thing. And you can see here, with the block moving slightly, you can see the red paint on there. So we climbed the shaft. A previous team had drilled a hole at the end of the shaft, but they hadn't been able to put a camera through to find anything. So our first mission was to get there, to go and deploy a camera through that hole. So you'll see here, this is when we get towards the end of the shaft, you'll see how it's working. So it has automatic cameras, automatic lights. So as you do different actions, it automatically shows you different things. So it'll show you what's moving, change the light so you can see what's going on. It's getting quite exciting now. We're right at the end here. So at this point here, my overriding thought is, don't hit the block. If you drove too far, if you drove into the end, you would knock yourself out of the shaft. So it's quite stressful here. How do we drive towards the end of the stone, but don't actually get knocked out of the shaft? You can see here's the end of the stone just here. We got there, we used our snake camera to map the front. The first thing we found was, one of the questions is, okay, you've got this tunnel, it's capped off. Is that being carved in, or is the end stone being added? If you look at the end stone, you'll notice here you have a chamfer on the end. That chamfer is normally used when you drop the stone in. So the first really good result from this was that end stone has most likely been dropped in rather than being carved as part of the stone. You'll see here we're putting the camera through the hole. I won't show the whole video, but we're very pleased that we lined up perfectly with the hole. You can see here we're going to gradually deploying our camera through the hole. Quite an exciting, stressful time. You can imagine it's going in. What we're going to find, no one knows. No one's seen it before, so it's the first time in 4,000 years that someone's been there, actually done that. You see the camera going through the hole now, so it's a quite exciting thing. Could be anything, we don't know. Almost like being in space. So yeah, that's the view from the other side we saw initially. So what we did, we used our camera, and we moved the camera around inside the space. What we found was these writing. Not been seen for 4,000 years. So when they built the pyramid, more than 4,000 years ago probably, when they built it, somebody drew these writing on there. It's the first time it's been seen for thousands of years. Amazing result. Another question was, on the front of the door, there are copper pins. The question was, how are them copper pins put in place? So you see on the outside of the stone you have these copper pins. Nobody before knew what they were being done for. If you go through the hole and you look back on yourself, you see these small hoops. So now we know there was a hole drilled through the stone and there are small hoops on there. But these hoops aren't used to lower the stone down. They're too small. The hole here is about 4 millimeters, not big enough to lower it down. So we know it ends in little hoops, but they are definitely decorative. They're not structural metallic things. They're definitely for decorative purposes only. So that's our result. This was about 3 years ago. Of course, since that point, Egypt had all these different issues and things going on. So we're working quite closely now to go back, and we're hopeful quite soon we'll finally answer the question. So just to summarise, we've climbed the shaft, we've looked through this first stone here, we've done a full survey here, we found the writing. What we haven't done yet, we haven't tried to drill this second stone here. There's a question, of course, is it drillable? It could be a massive block, it could be a small block, we don't know. So we're trying to work on that, and hopefully we'll find that answer soon. So obviously a very exciting project, a great example of how you can use robotics to find things that you couldn't possibly find in any other way. So that's kind of the most exciting one. But of course, the same technology can be used to inspect pipes. So people often say to me, okay, autonomous robots, what's going to be the most important discovery that happens, or the most important use of robots going forward? And actually, quite interestingly, my answer mostly is robots in pipes. It sounds ridiculous, but pipes are great for robots. So pipes for robots, they're defined, no worries about people being in the way. It's a simpler problem, but also the business case is huge. If you can get inside a pipe, if you can inspect it, you can remove leaks, you can repair it, you can stop from digging holes above the surface, causing roadworks, causing traffic jams. So although it perhaps sounds a bit dull, putting robots into pipes, to me it's going to have a massive impact and probably the simplest and best business case, if you like, for robots going forward. Pipes are quite hard though, so I mean straight pipes are simple. Pipes often have complex bends, complex things. So we're building robots that can go around in different configurations. For example here, we've got quite a complicated robot here. It has these pads on the top, pads on the bottom. It's interesting. Is that okay? It should, well, it's gone completely. try again. That was interesting, wasn't it? So technology is good. So, but yeah, so the idea is it goes around and it can twist. So in pipes, it's not only important to go in a straight line, it also must be able to twist and bend. In this case here, we can twist. So right now, it's going through the pipe, but also doing a corkscrew motion. So it's twisting as it goes up, which is quite important. If it's a metallic pipe, you can use robots that have magnets, of course, which is quite interesting. So here we've got our magnet robot to inspect mostly gas pipes, actually. So it's a small robot, magnetic wheels, but it can drive across things. It looks easy. It's really, really hard to be able to go from one surface to another surface. What you find is that it gets stuck on one or the other. This is a great robot that can go drive around different things. In that case there, I'll draw it again. In that case there, it's driving around in a square box. Of course, it would be a circular thing, but a square box is a worst case scenario because you have to transition from a flat surface to an upright surface. So you can see here, that looks easy. That's really, really hard because it normally gets stuck on one or can't grip on the other one. I should say is that we're very interested in how you can power robots. So we have some technology we're working on at the moment, which is using very high power radio waves effectively. And from that, you can harvest that energy on the robot itself, and then you can power them. The actual energy is very dangerous, so you couldn't do this here, for example, it would kill us all. But if you are going to inspect, for example, an aircraft engine, you could have a situation where you have an aircraft engine, lots of small robots, and you can just fire out huge amounts of this energy. And these little robots can take the energy from the big system, so you have robots that work for indefinitely, effectively. So it's a really great technology in industrial applications, but not in the real world because, of course, it's dangerous. So that's going on right now. Hopefully we have a very prototype maybe in the next year or so of small micro robots that can drive around using this power from these kind of things. So we're now on part 3, so bear with me, we're getting there I think, hopefully not too close to lunch for you. So the final one I'll go through is part 3, looking at restricted access. So just to remind you, so we've covered open access, we've covered confined spaces. This is quite an interesting case, so this happens a lot in kind of search and rescue scenarios where you have a challenge to get into somewhere, but once you're in there, lots of space. So for example, a house. A house here, you might want to get through a small entrance hole. Once you've got through that hole, on the other side, you can then go and explore and find things out. So most of these robots need to be quite small, maybe change their shape, change their size. People often say to me, okay, we want to do this. Let's just build a very, very long snake arm. We're going to explore a house with a robot. We don't want a mobile robot. We want a snake to go in there, to go and explore the house, a snake. They don't realise how much force you need to go and do that. So this is a snake arm here. It's a 12mm diameter snake arm. Inside that snake arm we have little wires. So you pull on a wire. As you pull on the wire, the snake arm will bend around. It can support its own weight under gravity, which is really useful. So great, this is 1.2 meters. Go and make one that's 10 meters, 20 meters. But the forces you require to do that are huge. So if you look at what drives this, you have an absolutely enormous thing here. So this thing here, it can lift a car. It's absolutely enormous. But you require that to be able to pull the cable hard enough. So this will move things here. Inside here is a cable. It'll pull a cable really hard and cause it to raise. Even with this, we can only lift a 20-gram payload at the end of the arm. So it's very, very strange. And in fact, in terms of science facts, if you look at materials, we can only go to 3 meters at this diameter. Beyond that, you can't physically get enough cable, the right kind of cable, because of course the cables must fit into a small size. You can't get the materials right to do that, which is quite a challenge. So we're building reconfigurable robots. So this robot here, of course, is a straight line robot. You drill a hole in something, you put it through, it can then reconfigure to become a more conventional robot that can go and explore. So in its straight line case, it can drive forwards, which which is interesting. Can't do much else. But once it reconfigures, it becomes a more conventional robot that can do useful things in the real world. It's all self-powered, no one's done that. By its own self, it can reconfigure. Then you can drive around somewhere, explore stuff. We actually have a more advanced version of that. You may have seen in the very first slide, the first video in fact. We've got a more advanced version of that now, which does more advanced things. So that's that one. We were asked to do a specific project actually to go and explore a house. If you're going to do that, in the UK, houses have set sizes of letterboxes, so let's use that. So we're trying to build a robot that can fit through a letterbox that could go and explore a house. It has a fixed size. The challenge here is it's quite narrow. The width is fine, but it's quite flat. So how can you do that? So this is one of my, obviously I'm working quite hard on my desk as I always do. One of my postdoc students here coming to see what I'm up to. So he's using our robot to go and explore through his letterbox. So you can post it to a letterbox. On the other side, it can reconfigure. So right now it's quite flat, you can't see much. It arches up, so you can use a camera to see what's going on. Better viewpoint camera there, you can see, so now you've got a better viewpoint, so you can see what's going on. And the same mechanism also can climb stairs. So it's quite a nice way of getting into a house, inspecting the house. This is mostly, for example, if someone might have fallen down, you want to see if they're safe. It's not a covert security thing because it's too big, it's too cumbersome. But it's good for environments where you want to check something without knocking the door down, for example. We're also building drones also that can go through holes. So in this case here we've got a drone that can reconfigure, so you can put it through a small hole, it changes its shape, and then you can fly around and you can explore things. So here's going through a small hole here. On the other side, it reconfigures and explores space. Of course, the challenge here is getting it back. So we can put it through the hole, that's fine. We can change its shape, that's fine. But how do you recover it? That's quite a challenge. So we haven't got there yet. We can use cables, of course. Cables mean it's restricted, so it's quite a difficult thing to do. Another challenge we're looking at is where the actual entrance hole is restricted. So right now I've shown you things that can go through beautiful open holes. That's quite common. In search and rescue though, quite often these spaces aren't beautiful and open, they're cluttered. So you can see here kind of a tsunami's here, lots of clutter here. If someone was injured on the outside here, they'd be rescued. So the real challenge is, how can we get right into the heart of that property, right in the centre here? How can we get into there? How can we find out if someone is inside there trapped? If you go in there as a person, you probably can't fit. And if you did fit, it might collapse on you. It's very dangerous. So ideally a robot that can get in there would be good. But what happens is that as you start to drive through, bits of loose debris collect. Imagine a big bulldozer. Bits of loose things collect in front of the robot, and before you know it, you can't move. So how do you do that? Well, how do you cope with that? So we were inspired by the European mole. This little mole here is an expert digging through the ground. It burrows through. We wanted to create the same kind of technology on a robot that can go into that kind of building and search and rescue environment. So you can see here, the robots, the little moles moving around. You'll see in a minute a video of it going through couscous, obviously an ideal material to test it, so this is the video from MIT. So you see it burrows, it pushes things out of the way, it can go around. And here you've got an X-ray through couscous, very natural for it, I'm sure, but you can see how it's burrowing through material. So we want to create that same kind of motion on a robot. If we can do that, it can enter a building and it can get rid of this debris that's surrounding it. So our vision was this, little robot, conventional robot, but it has these digging arms on the front, so how can you do that? So it works by kind of a digging motion. So if the robot's nose is here, it has to have arms that reach forward and pull backwards. So the push-out motion here pushes through the debris, and then as you pull back, you push the debris to the side, clearing a path for you to go forward into the system. I'm not going to bore you with the equations here, but we wanted a system that had motors inside the body If you have motors on the outside, they get covered in dirt. So imagine the case of the robot's here. This is the case just here. These are inside the body. We use linkages to be able to transmit that. So this is the tip here. And we can push out here. So you can imagine two motors here. These motors, they never rotate backwards. You notice here, they both go in the same direction. They get faster and they get slower, but they never change direction. And this tip here, you can see, the tip follows this kind of motion here. So it's quite a nice way of doing it. If you don't reverse direction, it means you're more energy efficient and also less wear. So it's quite a nice thing to do. So we built one. You can see one being built here in metal. Quite high force output. And you'll see here a video of it working. So the first thing it's doing here is pushing through some very light foam. We're doing this to show you the flow of material. The material here flows from the front to the back. That's what you want, so it's working that way. Quite high force output, up to 80 newtons, 8 kilograms, so it's very high force output. And you can see here, it's not designed to push bricks.